Right, good afternoon, everybody, and welcome again to UniCourse. This is we're looking at Unit 20, Digital Principles, and we're going to be looking at hints and tips for assignment 1. We're going to go through some of the theory. The presentation shall last around about 40 minutes, and at the end, you will have time to answer questions. So when you're looking at the assignment, you will see the criteria, as you can see on this slide. And this is just the what we tutors have to work to on our assignments. I'll let you have a quick look at that for a minute, and then we'll go straight into the presentation. So we're going to do an overview on each of the criterias. Now, what I need to explain to you is that to complete these assignments, you need to successfully complete the pass questions first. And then if you want to move on to the merit, move on to the merit. And likewise, if there's a distinction question on the assignment, which there will be, you can't just pass the merit and distinction. You have to pass all of them to get the full criteria. So on P1, we're looking at the explain and analyze the operation of a simple combination logic circuit. And what we're looking for you to do here is using a logic circuit shown in the assignment. You need to, 1, construct a truth table, Karnaugh Maps, and Boolean algebra expressions. And what I recommend, and I'll mention this right through the assignment, is to put together some draft copies, sketch things out. I'll mention using a simulator as well near the end, but a lot of this can be just done by just sketching the truth tables, maps out, and the actual logic itself. The next thing we're going to look at is the merit question here, and that's to analyze and optimize operational combination circuit. Most of the questions are based just round producing a logic circuit, Boolean algebra, the truth table, and the Karnaugh Maps. And here for the distinction question, we're going into a bit more details, but on this time, what you'll need to do is look at a logic circuit and redesign it. Now, throughout this presentation, we'll be looking at some of the theories and giving you some idea on what to do. What I also recommend, which I'll hopefully mention at the end, is besides using the UniCourse notes, is to also do some further reading as well, so that you can get another idea on how to look at Boolean algebra, logic circuits, and things like that. So let's first introduce you to logic. Now, for some of you, you will have some background into logic. So let's just sort of get ourselves up to speed. So here we've got a battery and we have 2 switches. And on our far right, we have the truth table. And as we can see here, that when we have them open, that the X, which of course is the light bulb, it will only illuminate when we have both of these switched down. Now, just a bit of background, in the early days before we had semiconductors, we would use relays, and even before that, we just used basic switches. And this is how the initial logic was developed. But today, we use large-scale integration. We have a lot of different types of chips, which will allow us to do many different logic functions. So, as I said, the light bulb will only illuminate when both A and B are switched on, and that is our very basic AND gate. So let's look at the next one. And what we have here is what is known as the OR gate. So you've got 2 switches, but instead of having them in series, we've got these in parallel with the light bulb. And as we can see here, with the truth table A and B, as long as you've got either A or B or both of them switched on, you will get the bulb to illuminate. And we know this is known as OR gate. Now, I'm going through the basics because it's important before we start moving on to more in depth of the logic. And you can build these sort of circuits on simulators, or you can actually use the logic gates as well. So I'll give you a minute just to have a quick look at this. Now, the next one we'll look at is what is known as the NOT gate. Now, this time we're actually looking at one of the logic gate symbols. In simplistic terms, it's known as a sort of inverter. So whatever we put at A, so if we put a logic 1 at A, step it up, the output will always be the reverse. As we can see the truth table here, that we'll get a 1 here and a 0 here. And we can see the waveform here, how they invert each other. Okay, so this is a simple gate, the NOT gate. And that's used quite a lot with a lot of logic circuits. And to tell us that it is this triangle here, we've got this little circle at the end here. And this is telling us that it is known as the NOT gate. What we're going to look at now is the 7 basic logic gates. And here in the UK, we can't often use the ANSI symbol. Overseas, possibly America, they use the IEC. And what we can see here is that these are the basic symbols for most of all the logic gates. So we've got the top one, which always start with the AND gate. And quite often the symbol always represents A and B. But when we actually do use logic, you can have 4 inputs, you probably can have 8 inputs. But most often not, we look at the symbol with just 2 inputs. And the simplest letters we use is for A as input 1 and B for 2. And usually we use X. You will sometimes see on outputs Y or Z, but quite often it's X. It doesn't matter really, as long as that when you do the Boolean algebra, when you do your truth tables, it's the same. And the IEC symbol is the same as well. So we've got the AND gate, the OR gate, the NAND, and you can see here the difference between the NAND and the AND is just there, that little circle there. The NOR, which again is the invert, we have the little circle there, which is similar to this, but it's inverted. And then we look at the XOR and NXOR, and then finally the inverter, which is a NOT gate. And these are the symbols we will use. And I would expect that when you are producing your assignments to use either, preferably use the ANSI one. If you sketch it out by hand and then you just scan it in, use these symbols here. If you're using an electronic simulator like Tina, not Tina, in MicroCap, Tina doesn't support it, but using MicroCap or Circuit Wizard or Circuit Lab, you should be able to get these symbols up, and then you do a screenshot of it as well. So these are the 7 basic logic gates. So let's move on to laws of Boolean algebra. Now, this is sort of a bit of mathematics, but I'm going to try and break it down to make it as simple as possible. For really going into depth, you'll need to do some further reading. And my advice, strong advice to you is to sit down with a piece of paper and just sketch things out and get it right in your own mind, that you understand a bit about it. But we're going to look at the basics of Boolean algebra this afternoon. So this is the first one, cumulative law. And what we've got to see, we can see this here, which is the plus sign, which is the or sign is equal A or B. And then we've got, it can either be B or A. It doesn't matter which way around, simple as that. And then we go on to the A dot B or the B dot B, and the dot stands for and you'll see more of it as we go through these slides. So that's what we can see here, and this is how it also can be written as well. And this is when we add to it where we've got a third input as well, which is a C here, and we can put the brackets around as well. And this is getting into a bit of maths, but as long as you break it down to simplify it, it shouldn't be too bad. This is the next law, and you can see here where we've got the A dot and the bracket B or C, and there we can see that. And these are very similar to what you use in maths, because if you take the brackets away, then you just got A and B and A and C, and then you've got it here on this one here, which is the A or B dot and C, and then if we use the brackets in this way, we get this as well. And this is where we distribute the letters. This is where identity law, okay, and this is where it can either A or A is equal to A and A is equal to A. You don't have to worry too much. As long as you've got the basics, understanding the basics of Boolean algebra, you shouldn't be too bad. And here's where we can reduce it down, or to simplify it down, where we've got the two A's and we can then reduce it down, and we get this at the end here. But these I will go through a few times just to get in your own mind, and you'll find these in the UniCourse study guide notes as well. And here is De Morgan's theorem. And when we get the line above the letter, that means to say that is either inverted or both A or B is being inverted. And you can see here where we've got the line. This is when you invert it, where we're actually adding a not gate to it. And this is where we have the line above it. So if you've got a line above the letter, it's being inverted. In other words, when we put it in, it will go from a 1 to a 0, or from a 0 to 1. It's inverting the actual inputs. And this is the final one here, which we use, and you can see where this is in. So you just, in your own time, just go through all these. As I say, these are all in the UniCourse study guide for this first assignment. So we can see here what letters we use, and for the Boolean statements, we often not use A or C, and that will indicate inputs. It's quite standard. You can form your own, but that is to simplify it. And what we use for the outputs is usually X or Y. And sometimes, and I've seen this in textbooks where they've used Q on the output. You sometimes see these on these JK flip-flops, things like that, which we're not discussing today, but usually it's X or Y. So here, let's look at it here from the Boolean algebra, and let's see how they equate. So we can see here, we've got X, as you can see, we're all using X is equal to A and B, with the dot there. X for the OR gate is A, and the little plus sign, which is OR. And then if we put the line above it, and you'll see when we see the actual gate itself, a little circle, this is known as the NAND gate. And likewise, when we've got the OR gate and we put a little dot on it, it becomes an OR gate. And these here are XOR, XNOR, and finally, you just see a little triangle with a dot on it. It is just an A is inverted, and we call this a NOT gate. I'll give you a couple of seconds to have a quick look. As I say, this video is recorded, so you can preview it again, and you'll look at through the UC notes. So here again, we've got more letters, and I'm just referring to what A dot B is. That is an and when we've got the what we should have here, A dot means it should be, that should be the and. So there's a slight typo error on that one. Don't worry about that. And you can see AND gates, the output logic 1 with the input A and B are logic 1. And if you've got like 3 inputs and it's an AND gate, all the inputs must be at 1. And where the AND gate gives that logic 0, so therefore if you've got the 2 ones on the input, we'll look at that a bit later on, and you'll find that you'll get the inverse, which will be a 0. Now, when we look at AND gates and when we look at the NAND gates, the N, that tells us that we're actually going to invert it from the AND to the NAND. And we'll look at the Boolean algebra expression. There'll be a line above the letters. And the digital logic for the NAND gate and the NOT are all opposed to the AND. And similar for the NOR gate, where we've got that has been inverted, and the NOT, which is just the inverter, and the XNOR, again, that is a NOT gate at the end of it. And as the saying goes, quite often what we do see, the clue is there will be a circle at the output of the actual gate. So the AND gate gives us an output of logic 1 only when both are at 1, and when you have one input which is a 0, the output will always be 0. So you could have, in theory, an 8 input AND gate, and if one of those inputs is a 0, the output will be 0. But if all the inputs are at a 1, then the output will be 1. Where the OR gate, it doesn't matter if 5 out of 6 inputs were 0. If one of them is a 1, then the output will be 1. And a lot of these logic gates, as we can start to see, are used in a lot of different types of electronic applications. And depending what you need to have to be open or not opened or closed. And usually the one I always give as an example is when you look at the car, when you open the car and you get into the driver's seat and you want to switch the engine on, there must be various things that must happen first before the ignition is turned over. Now the NAND gate, whatever we do on the input of the NAND gate, so if we've actually got 7 that are a 0 and 1 of the inputs is a 1, if the fact is we've actually got a NAND gate, then the output was going to be 1. So it's basically inverting what would normally be the input or the output of an AND gate. And likewise, the same thing for the OR gate. So you quite often notice as long as you've got at least one input with a 1, it would be 1. But if you then put the NOT on it and make it into a NOT gate, then you will get a 0. As I say, I'll let you have a quick look at that because it gives you time just to digest it. And we look at the XOR gate, and that is where you've got the only one of the inputs at logic 1, otherwise output is at logic 0, and the XOR gate. And these two they have their own sort of law they operate. But quite often and not, in the real world of electronics, the most common gates we use are the AND, OR, NAND, NOR, and NOT gates. We don't often see these, but they are used from time to time. As I say, the NOT gate we call an inverter. And that is a very useful gate to use. And in the world of electronics, when designers are working on it, and instead of actually redesigning it, they may use a NOT gate and then connect it up to an AND gate to get the actual NAND gate, instead of actually putting in a group of NAND gates onto the circuit board. Right, so we're going to look at Karnaugh Maps. Now, I'll start to explain that with these type of maps, it's not something that you always get to grips with it. And my recommendations is to draw it out yourself in your own time. You may find different authors have different approaches to it. UniCourse have an excellent chapter on these maps, but there's one or two other good web-based notes which you can look through. The second thing is, don't try to use more than 2 inputs to start off with, because it gets a lot confusing. Just work on the basics, which we're looking at today. We are looking at producing some additional videos later on, but hopefully with the video I've done today and the UniCourse guide notes, this should be enough for you to get you through the assignment. And also remember is make sure that you label up the note, your diagrams and some things like that. So we're going to look at this in a very simplistic terms, and we'll go from here. So what we have here is we've got the logic gate here. What we have is a AND gate. So that is the symbol. We've got 2 inputs, A and B, and we've got X as the output. And what we'll be using is, as we can see here, is this, the way we've set these zeros and ones out is, and we use a thing called the grey code, which we'll look at that very briefly. The grey code is a way that we can actually produce a set for each line. So 0, 0, 1, we can see how it moves up and down so that it doesn't get too confusing. In other words, you don't just populate your truth table randomly with different zeros and ones. You want to do it in such an order that it makes life slightly easier to actually understand. So what we've got there, we've got truth table in the center, and then you produce this Karnaugh map to the right, and then you produce a table. Now, because we were only using 2 inputs, then we only need to have A and B here, and then from the permutations of here, we realize that only when we get 2 1s, it gives us a 1 for the output. We'll look at some groupings a bit later on, but my recommendation is just to get to grips in the way that you put logic gate out, you put your truth table, and you put your map, and just work in an order like that. And when you're doing the assignment questions, just sketch it out and just go through it in your own mind how it is. Look at various authors on this area, and then hopefully you should be okay. And you can quickly work out what the outputs are. You don't need to simulate this, because once you understand how the gates operate, it's quite easy to work out how to set out your truth table and what will be expected on the output. So when you become familiar with that, that is useful, because when I used to work logic circuits many years ago, and we had these large circuit boards, and I was using a logic probe, I knew on the circuit diagram what the logic gate should produce. So long as that I knew that the input there was meant to be a 1 or 0, and there was an AND gate or an AND gate or OR gate, I knew with the logic probe what there should be in the outputs, and therefore that if it was doing what I was expecting to do, I knew that the logic gate was functioning properly. If it wasn't doing what it's probably not doing, it's either a faulty logic gate or there was no power to the actual logic chip. So let's move on here. So we're going to look at a bit more detail, and we've just got the same one here, and I'll let you read through this here. This is a box for every line of the truth table. It's binary values, in other words, is in 0, 1s. We're only looking at A and B, and there's a sequence of order. The X is the output here, and we can then enter the values, the output values. These are only the output values, not the input values. We look at the inputs here at the top, and that they're set out in a format, the grey code format like this. We're taking it from what we've got from the actual truth table. Don't try to sort of do it directly off there. It's easier to produce a truth table and then produce that as well. So if we decide to be a bit more adventurous, we can go on to 3 inputs, which we can see here. And as you can see, is the A and B remains on the top here. The C is underneath that diagonal line. And likewise, a 4 input, we've got A, B, C, and D. And as we get bigger, the amount of cells that we need more cells, and of course it gets a bit more complicated, and then we're looking at groupings, which we'll briefly look at a bit later on. But as I said, this is an area which you need to read through yourself in your own time, and you need to really look at it, because you'll see that in quite that these will make it like a cylinder type form. At first it looks a bit confusing, but you'll start to realize why they have that. Now, I mentioned the grade code, and this is the grade code where we can see that we use these so that when we produce the truth tables, it allows us to do it in an easier formatted way that we can then produce the logic inputs and then look at the logic output. So you use this as part of your inputs, and then you do that. And then on the left-hand side, which we can see here, we've got the binary coded decimal, BCD, which we can use to convert these into numbers as well. And you're starting off at 0, that's 1, that's 2, that's 3, etc. And you go down that. And I'm saying this is something which you can read through in your own time about the converting the BCD into decimals. So let us look at the truth tables and here. So what we've got here is we have the 3 input. We've got a 3 input AND gate, and we've got the OR gate here. And what you can see here is we've got the A, B, and C. Now, what we do is we produce the truth table, and there's a various ways. You can actually sketch it by hand, and then just literally say, right, well, I've got an input of 1 here, I've got an input of 1 there, what should I have at D? Okay, and that output from there will feed into here, into this OR gate. I'm using the X as the output. Now, the reason why we've included this D in here is because we've got outputs coming out these 2 E's, but the general Boolean algebra, as you can see here, is these letters over here, and that's the Boolean algebra statement. And you know what you want to do is produce a truth table. Now you can, if you want to just check that the output is what you think it is, you can actually simulate it, produce that on a simulator, either using Microcap or using Circuit Wizard or using Circuit Lab, and then look at results. Or if you've got something at work where you've got a one of these logic tutors, you can produce stuff like this and look at the output. But it's easy to draw it out, get a pencil and see what I've got 2 1s here. What are the output there? Right, put a little line, say it's an output with number 1. Okay, what we're going to do is, and as you change it, but the idea, what is recommended is create a truth table on one side of your piece of paper, and then using the grayscale to set the format of 0 and 1, and then you can see the output, and from there you should be able to see how the Boolean algebra is coming together. Now this looks a bit more complicated, but this is using De Morgan's theorem. I would look at this in more detail yourself and look at how it is, and this is by simplifying Boolean algebra. And as we can see here, what I said to you before, is the line above the letter is inverting it, and there's a line going right across it. It is inverting everything. So you got like a double inverting it, basically inverting and then inverting it back again. And like it's inverted a lot, but only the input A is being inverted and C is being inverted. Okay, so you could basically, if we're looking at a logic circuit, the input A will be going through a NOT gate, and likewise C, but all of it is all being fed and it's all been inverted, and what we call the OR gate facility here. So this is all going through an OR gate as well. And I would recommend that you slowly go through each one of these just to get an idea. As I say, time to just go through these and just give you an overview on it. But you should find these within the guide notes. So we're more or less nearly halfway through that. So we basically covered the basic logic. We looked at Boolean algebra. We looked at Karnaugh Maps, and we looked briefly at truth tables. What is important is that when you are creating your assignment, that you document it well, and you click as much information as you can, so that I can mark it. I can't mark it if there's not enough information there. So we're going to look at further hints and tips, and we're going to look at these various areas here, and then we've got a couple of examples to look at, and then you can refer back to your assignment. Now, one thing is important that when you are completing the assignment is that if you look down the actual assignment brief, as you look at the earlier questions on the assignment, they will be for the passes, and as you're moving further down, you're moving toward the higher grade part of the assignment. And quite often, as some of you have actually completed assignments for me, is what I'm very keen on, that the diagrams, the photographs are all annotated. And if you're using any reference to any other material that you reference using Harvard referencing at the end of the assignment. You never can produce too much material, but don't try to limit it too much. And you can also always contact me via email, things like that. So let's carry on. We'll look at the hints and tips on the assignment. So as you can see here, I've drawn it out in such ways. All right, this is from a screenshot from a simulator, and we've got here. This is the inputs here, okay. And what we can do there is we've strapped the two inputs. So basically, we've got made that into one. And sometimes in the real electronics, we sometimes do that. We have to sort of strap the gates together for various reasons. We don't want to leave one gate left open sometimes because of interference, and you don't want any static noise to create a pulse, which will give you a false signal. So we strap the two together, and what you've got there is you've got an AND gate there, and you've got a NOT gate there. So that comes here, so there'll be one in there. Now, when you've got these two gates here, and the same as here, and in the manufacturing world, when they're producing vast amounts of electronic circuit boards, they want to make it as cheap as possible. So what we've got here is we've actually got 1, 2, 3 different logic gates, and these would have to be in 3 different ICs, integrated circuits. So how could we simplify this? Think about it. We've got here an AND gate and we've got a NOT gate here, but in the world of the electronics, like the 7400 or in the 4000 series for CMOS, well, let's take the 7400 series. We can create. We can actually use a NAND gate. We don't need to use a NOT. We can use a NAND gate. So that will be, instead of using that has all been annotated. So here we're looking at the Boolean algebra, and here we have A and B, or A and C, or A and B or C. And there we can see the actual logic gate. And what I sometimes do is, when I like to design a few circuits, is I try to follow this and produce a circuit. So here we've got here an A and B. So we've got an AND gate there. And then we can say, right, okay, we've got we need 3 inputs. So we've got 3 gates here. And then we're going to OR it, which goes into here, and we can see that as OR gates. So we've got this is the AND, and this is the OR, and that is how it finishes off. Here is a very simple truth table, and on our right-hand side, and we're just using switches here to make to look at the gates. We're just using this LED here. So when the LED is turned on, it means it's a 1. When the LED is off, it's a 0. Quite often when you're using microcap and you're using the transit, you should be able to use the scope facilities, and you'll see a timing diagram where you'll be able to look at the actual logic outputs, which I produce here. I'm using the Karnaugh Maps here, I've just produced the AND gate and the X, and then we've got this as the actual what comes on the Boolean algebra, as simple as that when we're using here. So this is from the Yes.
There's a problem with this signal.
Just stopping for a second.
Switch off your.
Sorry about that, guys. We just had a technical thing here, so you're all still there. It wasn't your end, it was our end. So I'll just go through this again. We're looking at using the map. We just sketched something out. And if you produce, handwrite it out, and you've got everything annotated, it'll be a bit more elaborate in your own assignment. As long as you've got it, we can see all this, then you shouldn't be a problem. This is just an example. And here we're using the expression again, just looking at X, which is equal to A or B, and make sure it's all clearly written out, and you shouldn't have a problem onto it. Then, of course, we've got the truth table, and just put on the top there, truth table, so that I can see that. And you know, as long as it's all well annotated, there shouldn't be a problem. And we use output, which is a Z. Don't put A, B, and C. Don't put C there because we classify C as an input. X, Y, Z is X and Y is usually input. Z. It's not a problem if you want to use that. I'll leave it up to yourselves how you want to. The AND gates here, and you've got the NOT gates here. You can actually convert all this in just using NAND gates. That remains the same, and you just basically take these two out and put a NAND gate in, and instead of using 1, 2, 3 chips, you only need to use basically 1 chip for it to produce the NAND gate. And in electronic manufacturing terms, it works out a lot cheaper. So what is important, and I always say this, make sure the diagram, sketches, photographs, schematics are all annotated, a description, construction, and Karnaugh Maps, and you can test it. It's not too bad with the circuits you've got to do in your assignment, but a simulator you can use. The simulator is useful if you want to screen on there, but I'm quite happy for these sort of questions for you to do sketch it out, and that's on as well, and your outputs. So
can you repeat the last time because the internet cut?
Right. Okay. So we're gonna go back a few slides because we had a problem. So we're just going to go back just to, right, we're going to start it again, just so that we've got this recorded. So sorry about this. We're going to just quickly look again at the Boolean algebra expression. As you see here on the left-hand side, we got A or B, and on the right, we've got the truth table. We are using A and B as the inputs, and in this case, we're using Z. As I said, you can either use Z or you can use X and Y as your output. I wouldn't use C because it looks like it's an input. So what we're going back to, circuits, as I said, the manufacturers will be very keen to simplify the circuits. So what we've got here is we've got an AND gate, a NOT gate, and an NAND gate. So we say we want to use a NAND gate. So what we can take these out here. We can just use a NAND gate, and basically instead of using 1, 2, 3 chips, we'll just use 1 chip, because you should be able to get the enough NAND gates in 1 chip to be able to do the same as what we've got in here. Okay, so that's that. And as I say, what is important is when you are producing your assignment evidence, make sure that everything annotated. In my case, I've just put this. You don't have to put the inputs. I've just done it just to give you an example. And we've got the outputs, put some lines on it. And if you've got some information that you're using from some notes somewhere, you want to make it your own piece of work. So it's important. And this goes right across all the assignments that I am marking. And you'll do this right across, right through all the assignments. So you make sure everything is all annotated. Here, we're just going to look at one other example. Is when you've done the Karnaugh Maps, this is where we're going to, you've got your truth table, and here you can see we've got the groupings here for A and B, and this is something that you need to look at in your own time. We've got 3 inputs, A, B, and C. So we've got A and B here, C is here. We've got 0, 0 here, 0, 1 here, and where we've got the ones, they're grouped together, and that allows us to form the Boolean algebra. And it's something which you need to go in your own time and go through it and just rewrite it until you are happy with it. As long as you've got the basics, then you shouldn't have a problem. And you see here, we've just got here the grey code, and this is the truth table at the bottom here, which is following from here. So this, you produce this, produce the truth table. From the truth table, you can then look at the maps afterwards. So you can see here in a bit more detail here, and this is breaking it down. And saying you need to just carefully go through it a few times to get to grips with it and look at where the groupings are. You're only looking at the groupings for the ones, not for the zeros. The zeros were not necessary, not needed. It's just the groupings of the ones, and that is where it's, so where the door shuts, so where the light comes on, that is what you're looking at. So we'll come to the end of it. It will be on Moodle at some stage, so you'll be able to review it again. We are looking at producing some more shorter videos, which will go into a lot more detail, which will be done by Mike Lopez, which will be hopefully done in the next few weeks. But you can look through the notes. If you've got any questions, you can always send me an email, and I can send you some guidance on all the notes that you can look at as well.